Hi everyone, in this video, we're gonna dive into PCA, its principal component analysis, and we'll break it down from a few angles. First up, what's the motivation behind using it? Then we'll get a bit of geometric intuition going on. After that, we'll pick at it from an algebraic angle. And finally, we'll check out a real-world example using a Kaggle dataset called US Stock Fundamentals. Alright, so let's start with a big question. Why do we even need PCA? If you take a look at the real datasets, especially in something like operation research or machine learning, they almost never live in just 2 or 3 little dimensions. You've got dozens, sometimes hundreds or even thousands of features, and a bunch of them are basically doing the same job. You might have 10 different financial ratios that are all explored at the same time in a crisis, or 5 risk scores that always move together. On paper, they are different features, but in practice, they are reacting to the same underlying effect. So we end up with redundant information, and it's all just too high-dimensional to visualize. Our brains are stuck in 2 or 3 dimensions, and beyond that, it's just numbers, which makes models slower, noisier, and easier to overfit. Basically, they are trying to learn in a huge, messy space where a lot of directions don't add much real signal. Now let's use the picture to really lock in the 2-dimension intuition. On the left, imagine we have these mostly horizontal strip of points that spread out along the axes, but vertically they barely move at all. That means feature 1 is carrying almost all the information, and feature 2 is basically just a flat noise. If you deleted the y-coordinate, you wouldn't lose much information at all. In the middle, it's the opposite. It's a vertical strip. Everything changes in the y direction, and along the axes, the data are squeezed into basically one column. So in this case, feature 2 is the useful one, and feature 1 is just an actual dimension we don't really need. The interesting one is a plot on right. Here the points from a slanted strip, neither the x-axis nor the y-axis is aligned with the data. Both coordinates are mixing 2 things together. The real signal, which is movement along the strip, and the small wiggles across the strip, which is almost noise. Now look at the red points in the middle of the cloud. That's the center of the data. The average point in PCA, we always center the data, which just means we pretend this red point is the new origin. We shift our coordinate system so that crosshairs sit right at the center of the cloud. Once we've done that, we draw 2 dashed lines. The gray dashed line that goes along the slanted shape is our new x-axis, or PC1. It's aligned with the direction where the data vary the most. The dotted line is perpendicular to it is our new y-axis, or PC2. Together, they form a new coordinate system whose origin is at the data center. In a new system, the first coordinate tells you where you are along the strip, lots of information there. The second coordinate tells you how far off the strip you are, just a small leftover noise. So in this situation like this, we basically keep the PC1 and almost ignore the PC2. The data effectively go from 2 dimension down to the 1 dimension. And that's one of the key jobs of PCA, dimension reduction. The key point is we didn't move the data, we just rotated the axes and then kept the direction that actually mattered. Let's upgrade our 2D picture to 3 dimensions, because this is where PCA starts to feel like actual magic instead of just rotating a line. Imagine every point now has 3 features, and all these gray dots form a kind of slanted tube in space. It's not filling the whole 3D box, it's more like a long, skinny cigar floating in the air. Along one direction, the clouds stretch out a lot, but if you look in other directions, it's barely spread, just a tiny jitter. Now, the red line you see here is PC1. The way to think about PC1 is simple. Take a line through the center of the cloud and mentally spin it around in every possible direction. For each direction, imagine projecting all the points onto the line and asking, do the projected points spread out a lot, or do they collapse into a small clump? The direction where they spread out a lot is PC1. It's the single direction that captures the most variance, the most signal. Cool, but PC1 doesn't stop there. If we only kept PC1 with compressing from 3 dimensions down to 1, sometimes we want to go from 3 dimensions to 2 instead, so we keep a second direction. Here's the idea for PC2. Once PC1 is chosen, PC2 has to be perpendicular to it, otherwise, with just repeating information we already have, we look at the plane that's perpendicular to it, project all the points onto the plane, the green points, and find the direction in that plane with the most spread. That's PC2. PC3 is whatever direction is left that's perpendicular to both PC1 and PC2. In 3 dimensions, there's only one such direction left. In higher dimensions, it's the same idea. PCA keeps carving out what's left, always choosing the direction with the most remaining variance, and making sure each new axis is orthogonal so we are not double counting. In one line, PCA is just repeating ask, what direction explain the most spread that we haven't already explained. Okay, now we are in the proof part. And I promise this is not the kind of proof where you have to worship the mascots. We are just going to translate our geometric story into clean algebra and show one key fact. In the end, PCA chooses the eigenvectors of covariance matrix. First, let's restate the setup in plain English. We start with raw data points, which I call x to 1 up to x to n. Each point lives in d dimensions, so you can think of each one as a d-dimensional feature vector. The very first thing PCA does is center the data. We compute the average of those raw data points. There's one sample mean, and then we subtract this mean from every single sample. After this step, the average of new points is exactly 0. Geometrically, we've just shifted the coordinate system, so the origin now sits right in the middle of the cloud of points. Next, we stake all this center sample into one big data matrix called X. Each row of X is one center data point. From this matrix X, we build the sample covariance matrix, which called sigma. Take X transpose, multiply it by X, and scale by 1 over n. The result is d by d matrix. So what does the covariance matrix actually represent? You can think of sigma as a compact summary of how the data spreads out in every direction. The diagonal entries tell you how much each individual feature varies by itself. Those are variance. The off-diagonal entries tell you how pairs of features move together. Those are covariance. On top of that, sigma has very nice structure. It's symmetric and positive semi-definite. It's normal human language. That means its eigenvalues are real and it has an orthogonal set of eigenvectors. That nice behavior is exactly what PCA is going to explore. Now we can describe the goal of PCA. Using this notation, we want to find k new axes, k new directions, so that when we project our data onto those directions, the total variance of projected data is as large as possible. Algebraically, we collect those k directions into matrix W. Each column of W is one direction, and we require the columns to be orthonormal. That just means each column has length 1 and all columns are perpendicular to each other. Once we have W, we project original data x down to k dimensions by multiplying J equals x times W. So J is the data expressed in the new coordinate system. If you look at the covariance of J and add up the covariance of all k new coordinates, you get the total variance in a low dimensional space. On the slide, the total variance is written as 1 over n times the trace of J transpose J. After plugging J equals KW and doing a bit of algebra, this expression simplifies to the trace of W transpose times sigma times W. So we can write PCA as a clean optimization problem. Choose an orthogonal matrix W to maximize. That is the algebraic version of our earlier geometric story. Find k directions that captures as much spread as possible. Now we prove that the solution is given by eigenvectors of sigma. We'll do it in two ways: an eigendecomposition proof and a Lagrangian proof. So the method 1. Eigendecomposition. Because sigma is symmetric and positive semi-definite, we can diagonalize it. That means we can write sigma as V times lambda times V transpose, where the columns of V are eigenvectors of sigma, and lambda is a diagonal matrix that contains the eigenvalues. We sort those eigenvalues from largest to smallest along the diagonal. Any orthonormal matrix W can be written in an eigenvector basis as W equals V times Q, where Q is another matrix whose columns are also orthonormal. If we plug W equals VQ into our objective, the trace of W transpose sigma W becomes the trace of Q transpose lambda Q. Because lambda is diagonal, the trace is just the weighted sum of eigenvalues, where the weight comes from the squared entries of Q. The normality condition on Q tells us that the total weight we can spread across all eigenvalues is exactly K. To maximize the weighted sum, when eigenvalues are sorted from largest to small, we should put all our weight on the largest ones. In other words, the best choice of W is simply to take the eigenvectors corresponding to the largest eigenvalues. That's principal component 1 through principal component K. Method 2, Lagrangian proof. For second proof, we zoom in on just one direction first. We take a unit vector W, so W has length 1. If we project the data onto this direction, The variance along W is W transpose sigma W, so the first principal component is the solution of a simple optimization problem. Maximize W transpose sigma W subject to constraints. The norm of W is 1. To handle these constraints, we write down a Lagrangian variance term minus a Lagrangian multiplier times W has length 1. When we take the gradient with respect to W and set it to 0, the stationarity condition tells us sigma times W equals lambda times W. That's exactly the eigenvector equation. So any optimal direction W must be an eigenvector of sigma with eigenvalue lambda. And to maximize the variance, we pick the eigenvector with largest eigenvalue as our first principal component. For the next components, we add actual constraints that each new direction has to be perpendicular to all the previous ones. If we repeat the same Lagrangian argument with those orthogonality constraints, we again end up picking the eigenvectors of sigma ordered by decreasing eigenvalue. So both methods point to the same answer. PCA picks the top k eigenvectors of the covariance matrix. Finally, let's talk about the explained variance ratio, which is the thing people plot all the time. The total variance in the original d-dimensional space is simply the sum of all the eigenvalues of sigma. The variance captured by first k principal component is the sum of just the top k eigenvalues. So the explained variance ratio for k components is the sum of the top k eigenvalues divided by the sum of all eigenvalues. This why eigenvalues show up everywhere in PCA. Each eigenvalue tells you how much of the total variation is explained by its corresponding principal component. And that's the whole algebraic story of PCA. Center the data, build a covariance matrix, pose an optimization problem, and the solution turns out to be take the eigenvectors with the biggest eigenvalues. Alright, now let's finally look at a real-world example. Because up to this point, we've only talked about PCA in theory. The obvious question is, does PCA actually help when the data is messy, huge, and full of amazing values? To test that, I'm using a Kaggle dataset called US Stock Fundamentals. And just to be clear, these are not factors in the traditional asset pricing sense like value or momentum. They are raw accounting indicators, literally the line items that companies report in their financial statements. So it's fair to call them fundamental features, but they are not engineered signals. They are just the raw ingredients. The first thing I do is to load the dataset from my Google Drive. Each row in this table corresponds to a company and an indicator, and the columns contain the reported values from different years. Once I run a few quick sanity checks, the scale of problem becomes obvious. There are about 9,600 companies and more than 8,500 indicators. In other words, the feature space is enormous, but the bigger problem is coverage. Most indicators are missing for most companies. So even though it looks like you have thousands of features, almost none of them consistently available across firms. To work out late, I restrict myself to a single year and look at the cross-section. I pick 2014 for the year. I compute the coverage of each indicator. Basically, how many companies actually report late indicator in 2014 divided by the total number of companies. The distribution is extremely skewed. A huge number of indicators appear in fewer than 1% of companies, and only a very small slice is widely reported. So I said a coverage threshold is 30%, meaning I only keep the indicators that exist for at least 30% of firms. After applying this filter, I'm left with 71 indicators. It's still high dimensional, but at least it's not hopeless sparse. Next, I reshape the dataset into the matrix form that PCA needs. Each row becomes a company, each column becomes one of the 71 indicators, and the value are the row 2014 numbers. Even after the filtering step, some values are still missing, so I clean the data in two ways. First, I drop companies that are missing indicators. And I require each company to have at least 80% of the 71 features present. After this filtering, I'm left with 1,241 companies. Second, I impute the remaining missing values using median of each column. I use a median instead of the mean because accounting variables often have extreme outliers, and the median is more stable and robust. Now I'm finally ready for PCA. This is the only part where I slow down a bit and connect the code back to the math we discussed earlier. Before running PCA, I standardized the features with standard scalar. This step is absolutely critical. Different accounting indicators live on totally different numerical scales. Assets and liabilities are giant dollar amounts. Earnings per share is tiny. Tax rates are percentages. If we skip the scaling step, PCA will simply latch onto the variable with the biggest numerical magnitude, and the whole analysis becomes meaningless. So the correct pipeline is feed the scalar on the training data, transform everything to zero mean and unit variance, and then run PCA on a standardized matrix. Once I run PCA on all 71 standardized indicators, and these results mirror the theory almost perfectly. The first principal component alone explains about 33% of the total variance, which is huge amount for a 71 dimensional dataset. That tells you immediately that the indicators are highly correlated and extremely redundant. When I switch to a more practical setting and tell PCA to return through components to explain 90% of the variance, it ends up keeping about 20 components. That means PCA shrinks the feature space from 71 row indicators down to only about 20 uncorrelated directions, while still preserving almost all of the overall information. The script plot makes this visually obvious. It drops sharply in the first few components and then flattens out, which is exactly what you see when the intrinsic dimension is much smaller than the row dimension. But the real question isn't whether PCA compresses the data. The real question is whether PCA helps with prediction. To test this, I built a simple supervised task, predicting net income loss from the other indicators. I split data into a 70-30 chain test split. I feed the scalar only on the training set and use it to transform on the test set. I do the same for PCA, feed it on the training set and then apply the mapping to the test set. This is really important because fitting PCA on the test set will lead the information from test to chain. With the data properly prepared, I feed two rich regression models. The first model uses all the original standardized features, so that's the baseline model. The second model uses the PCA features, the 20 principal components that explain about 90% of variance, and the results are surprisingly strong, using all 71 original features. The test R-square is around 0.74, but when I train the model on the PCA components, the test R-squared jumps to around 0.825. PCA doesn't just compress the data, it actually makes the model generalize better. The reason is that these accounting indicators overlap massively with each other, so multi-collinearity is everywhere. Ridge regression helps, but PCA takes it one step further by rotating the feature space into independent directions and throwing away the low variance directions that mostly behave like noise. One honest caveat is that PCA is unsupervised. It doesn't know what the target variable is, so in some datasets, the predictive signal might sit in a low variance direction. The PCA could actually hurt performance. That's why you don't rely on PCA blindly. You compare before and after performance, just like I did here. But in this dataset, the conclusion is pretty clear. When you are dealing with high-dimensional, noisy, high-correlated fundamental data, PCA gives you a cleaner and more compact representation, and they can even improve downstream predictive performance. So the combination of compression and better generalization really shows how PCA can shine in the real world. Alright, that's the full PCA story: intuition, proof, and a real dataset. If this helped, please hit the like button and subscribe, because I'm going to keep posting videos on machine learning and operation research with a focus on intuition and real examples. If there's a topic you want me to cover next, or you are interested in collaborating, you can reach me through my email in my channel bio. See you in next one.